All right, class. I think that I'm recording and I'm going to see how this all goes. We really left off with AC network theory. That's where we're going, which really is exactly the same as DC network theory, except for the fact that instead of the current only flowing in one direction, it flows back and forth like a wave, flowing back, flowing this way, then flowing that way. And so that's what we want to look at. And we want to basically just see the difference between the various different waveforms and look at what type of response the individual components are going to have. So let's say that we have a wave. And I'm just going to draw a wave here. And I'm going to draw two waves, actually. I'm going to draw a sine wave, right, that looks like this. And why do I say that's a sine wave? Because when we look at the unit circle, I'm just going to draw the unit circle over here. When we look at the unit circle, we know that this is the cosine axis, and we know that this is the sine axis. And so in the unit circle, what happens when we're looking at the sine? Well, as we know, the sine of 45 degrees, if I was to go over here on the sine axis and look at the sine of 45 degrees, well, that would be approximately the same as the cosine of 45 degrees, wouldn't it? You know, there would be our 45-degree vector, and they would be about the same. And we know that the sine down here, the coordinates of this, is going to be 1, 0, right? So if the cosine is 1 and the sine is 0, then that's where we are right here at the beginning of the cycle. And that's why, you know, going around here in 360 degrees, and of course this would be 360 degrees, and it would also equal 2 pi radians, right? And when you do the math there, if you want to find out how many, you know, degrees are in a radian, I think we've already figured that out, and that was 57.3. So looking at this, this would be a sine wave because it goes up to a maximum at 90 degrees. This would be my 90-degree mark. And then at 180 degrees, it goes back down to 0, and we can sort of see that as we go around this circle here, going up to the 90-degree mark. There would be my 90 degrees right there. That's going to be at a maximum, right? Sine is going to be at a maximum. Started out at 0, but now it's at a maximum. And on the unit circle, of course, that maximum would be 1, 0. And then as we keep going through and going to 180 degrees, which would be right here, 180 degrees, we see it goes back down to a minimum. Then as we go through another 90 degrees, which would take us right down here, and of course that would be a negative maximum, right? So we would be at -1, oh, excuse me, -1, 0 here, and then 0, -1 at 270 degrees. And then we go right back to the beginning again, and you can see how this would then just continue on, similar to how we started over here. So we've completed one cycle by going from here all the way to here. And of course, at 360 degrees, again, we go back to sine being 0. If we were to look at a cosine wave, and, you know, looking at this cosine wave, we'll extend it a little bit beyond the thing here, but the cosine wave would look like this. Let me extend this line out a little bit further so we get a little bit more. It would look like this, wouldn't it? When it completed its first cycle. And why do I say that this is this is a sine wave and this is a cosine wave? And why do I say that? Because look at where we start here. We start at 1. So we start at 1. And of course, the cosine is 1 at 0 degrees. So at 0 degrees, the cosine is 1, just like the sine at 0 degrees was 0. And then we go down to 0 at 60 degrees. And isn't that what's happening here? We're going from 1 back to 0 because the coordinate of this is 1, 0. And then we go down to a negative, and then we go back up to 0, and then we finish it off with 1 again, just like this, just going around the unit circle, just like that. And again, this would be my 90, this would be my 180, this would be my 270, and this would be my 360 degree mark. So this is a sine wave and this is a cosine wave. The two things that these have in common, though, is that they're both sinusoidally varying And so since they're sinusoidally varying, whether we're looking at it as a cosine wave or a sine wave. Now, I want to extend this out here a little bit. Let's go back here. Now, if we go back to the beginning of that dotted line, we can see that we've really shifted the cosine wave 90 degrees, haven't we? And all of a sudden, shifting that cosine wave 90 degrees, well, actually, shifting at 90, if I shifted that, I'm saying if I shifted the sine wave 90 degrees, then the sine wave would become a cosine wave. And let's see if that's true. Is that true? Is the sine of theta plus 90 degrees equal to the cosine of theta? I like to do that with, you know, 270 degrees. Now, is the sine of 270 degrees plus 90 degrees equal to the cosine of 270 degrees? Well, 270 degrees, 90 degrees, that'd be 360 degrees. And so the sine of 360 degrees is going to be 0. And is that the same as the cosine of 270 degrees? The cosine of 270 degrees is also 0. Does that work for all of the things that we've got here? Well, let's just see. Let's go up to the sine of 90 degrees, or sine of 90 degrees plus 90. That's the sine. That would be 0, and the cosine of 90 degrees is 0 too. How about the -1 then? If we did it for 360 degrees. Well, the sine of 360 degrees plus 90 would be the sine of 90 degrees, which would be 1, and that would be the cosine of 0, which would be 1 as well. So you can see that that's what we're really talking about, is that this wave, if I were to translate this wave phase-wise, 90 degrees, that wave would then have this part right here starting right here, right? And we would have chopped off this section right here, so that if I have a sine wave and I shift the sine wave to the left, and that's what you're wondering right now. So if we take a wave and we shift it to the left, right? That means you're adding that angle to the wave. If we shift it to the right, that means that you're subtracting that angle from the wave. So do you see what I'm saying now? If I take this sine wave and I shift it to the right, to the left, did I say it? I've got the right on my mind. And I shift it to the left, where this point right here now goes from the 90 degree point to the 0 degree point, then that is a positive shift. you can see that if what we've got here too. What if I was to take this cosine right here, this cosine wave, right, and I was to shift it to the left? Now, actually, I've drawn this the wrong way. It would this would then be here, and it would then start off here like this. I'm just going to actually draw the wave shifted to the left 90 degrees as the dotted line, right? Can everybody see that dotted line? And in fact, I should just cross that line out. I don't even know what I was doing there. So you can see what happens here. This would be a negative sine wave, wouldn't it? Does everyone see that? If I were to take this cosine wave and I was to shift that to the left 90 degrees. So let's do that. So I've got a cosine wave and I've got theta plus 90 degrees. That means I'm shifting it to the left 90 degrees. What would it look like? Well, now it would come down here and it would be the dotted line. And you can see that the dotted line is a mirror image of the sine wave that I have up here, right? So it'd be a negative sine wave. So equals minus the sine of theta. Does everyone see what I'm saying there? So let's just look at this. Let's take a negative number. Let's say the sine of 270 degrees. So if I've got minus the sine of 270 degrees, that should equal the cosine of 270 degrees plus 90. Right? So let's just see, the cosine of 360 degrees would be 1. And minus the sine of 270 degrees, well, minus a minus 1 equals 1. Does everyone see how that works? Okay, well, I'm not sure how long I have gone on with this brief explanation of the sine and cosine waves and sinusoidally varying waves. But what I really want to do is I want to get into the various responses of the current and voltage responses of the three main components that we use in AC circuits. We of course use these in DC circuits too, but they behave much differently in AC circuits than they do in DC circuits. And so that's what we want to think about now. So I'm just going to draw a line sort of dividing our discussion here about the sinusoidally varying waves and how the unit circle, I'll put unit circle up here. And I may be able to actually scan these in and send them out to you too. So that wouldn't take much. Now, what I want to do is talk about what are the responses, the resistive responses, the reactive responses, and those together, of course, being the impedance response to the three different components that we use in circuits. And I want to point something out about impedance. If we look at impedance, now impedance is a complex number, isn't it? It's R plus JX. R being resistance and X being reactance. I'm not even going to write resistance because I think everybody knows from the DC network theory that we've done that R represents resistance. X represents reactance. And you're probably saying, well, I guess reactance really isn't a loss, an energy loss, but that's not true. It is an energy loss, but it's an energy loss in a different way, and I'll explain why. If you look at resistance, and you're looking at a waveform that is propagating over a very long distance, and its resistance, right? Here's what happens to the waveform. And of course, it's a decibel loss in amplitude, isn't it? And I'm oversimplifying this, of course, but I'm just trying to show that the wavelength stays the same, but the amplitude changes. And so that is how a waveform loses power, right? Loses energy as it travels along a long distance. Let's say that its distance is 10 kilometers, right? And it's on a coaxial cable or something. It's going to lose that energy. But how does reactance come into play for loss of energy? If you were to lose energy in a purely reactive manner, you would lose energy like this. You're probably saying, hey, it doesn't have lost any energy. The amplitude is all the same all the way along. That's true. But look at the wavelength, right? Right here, my wavelength, right, between those two peaks right there, if that's my wavelength one, right, is much shorter than wavelength two, which would be, let's say, here, right? Does everyone see that? Now, what does that mean? Well, energy is equal to Planck's constant times the frequency, right? And so if I have a longer wavelength, then I'm going to have, and of course, usually we're traveling at, whatever propagation velocity we have, but propagation velocity for a waveform is going to be frequency times wavelength, right? Frequency times wavelength equals velocity. So when we see the wavelength change here, we can see that the frequency is also changing, right? Because the frequency, of course, is going to be equal to the velocity, the propagation velocity divided by the wavelength. And if the wavelength gets larger, then the frequency gets lower, right? So if the wavelength is getting longer and bigger, then the frequency is getting lower. Frequency is getting lower means that the energy of the waveform is getting lower. And that's what you really want to think about, right? So both ways, both reactance and resistance claim energy from a waveform. That's what you should realize. Dependent upon how the whole thing is laid out in a circuit, you may end up reclaiming some of that energy, maybe losing it on one cycle and gaining it back on another, whatever. We'll see. Now, so that's what I wanted to point out here. And so let's look at the three different impedances. For the impedance of the resistor, we know it's zero reactance, right? So we have zero reactance in a resistor. So if I was to write this out, that would be resistance plus J0. And what are my units? My units are going to be in ohms, right? So I'm always going to be in ohms. Impedance is in ohms, resistance is in ohms, and what do you know? Reactance, guess what, is in ohms too. That's right. Now, when I look at an inductor, and let's draw the three different schematic. Of course, this is my resistor, and then my inductor looks like a loop. And the reason that it looks like a loop is because that's how an inductor is made. Usually you'll have either a hollow core, which would be an air core inductor, or you'll have um, a steel core inductor. And of course, that's to help with the magnetism, because such high permeability in electrical steel that allows a greater magnetic field to be created by the inductor instead of having a hollow air core. The difference can be almost 10,000 between the permeability, the relative permeability between electrical steel and air. So, that's an inductor anyway. And then, of course, the capacitor, which is two plates, and that's very descriptive of what a capacitor really is. So let's look at the impedance of an inductor. Now, the impedance of an inductor in reality does have resistance, but in a purely theoretical inductor that was made with wire that had no resistance, you would have no resistance. So for a, but there, we're going to claim that for this theoretically great inductor that there is no resistance, right? But there is reactance. I'm going to say X sub L, but then I'm also going to take this extra space here and I'm going to say that it's 0 plus J omega L, right? And what is omega? Omega is the angular frequency. And you know, we've said this before, and I've always said this to all of the students that I teach AC network theory too. I say omega, you say 2 pi f. And so this is where, and this is so useful in all aspects of engineering. You know, you have to learn the basics. And both in mechanical engineering as well as electrical engineering, we use angular velocity, right? Radial velocity, angular velocity. And what does that really mean? That really means if you take this little arrow here and you are rotating it around this circle, and we know that it just goes through a cycle, doesn't it? Over and over and over and over again. Well, how many times is that going to go around there? Right, and there you go. There's the 2 pi. And what does omega really stand for? Let's just look at that. Omega is 2 pi radians. Remember that we're working in radians here, right? Unless you can change whatever it is in radians back to degrees, you better change your calculator too. So I've got 2 pi radians per cycle, right? And then I've got F, which is cycles. And by cycles, what do I mean? I mean a full cycle. I mean going from here all the way to here. I mean going from here all the way around the unit circle back to the beginning again. One cycle. F cycles per second. And I think everybody can see that the cycles just cancel out. And that gives omega radians, or, you know, dimensions of radians per second. Now, you're probably also saying, hey, I also, in my mechanical engineering, we know radians per second too, and that would be if I took a disk, right? If I took a disk and then I started rotating that disk at certain speed, right, in a circle. And we usually think of that as revolutions per minute. And now you're probably thinking, okay, well, hey, revolutions per minute is not an engineering unit, is it? No, you can't use revolutions per minute in mechanical engineering any more than electrical engineering. But that is, when we say revolutions per minute, that is omega. Revolutions per minute, turning that into radians per second is pretty easy, isn't it? Let's just do that math. So if I've got revolutions per minute, what would I have to multiply it by? Well, we know that there are 2 pi radians per revolution, right? I hope you're taking good notes, although I'm writing this down, so you probably are writing it faster than I am. And then minutes, we've got to take care of those minutes too. So I've got 1 minute equals 60 seconds. And you know, you can almost see the 2 pi radians is 6.28, isn't it? And 60 is about 10 times that. So really, we're going to be dividing this by 10. That's a good rule of thumb. If you ever, you know, have revolutions per minute and you want to rotate them into radians per second, you're going to end up dividing by 10 approximately. Now, I think that 1,400 revolutions per minute, I think that equals 147.12 radians per second. I don't know why that's stuck in my head, but I'm just going to actually plug it into my calculator here because unlike you guys, I am really fast with my calculator. And the answer is yes, I am exactly right. That is correct. So that's just a little example. Now, let's get back. We've taken care of the impedance of the inductor and the impedance of the resistor, and we've talked about what omega is, and of course L is just the inductance, let's say a 10 millihenry inductance or something like that of the inductor. So let's look at capacitance now then. So I've got capacitance. I've just realized I should probably switch this book around. I've got capacitance, and that also, a pure capacitor, and this is much actually closer to reality than the inductor, because the inductor has huge windings of, thin wires, so that's obviously going to cause some resistance, isn't it? Whereas the capacitor is really just two plates separated by a dielectric, and that makes this much closer to reality. And so this is 0 plus j x sub c. But this is where x sub c, where I teach this differently than other people teaches this. And this is what I'm going to say. X sub c equals minus 1 over omega c. And you'll see people that teach it differently. But I like to teach it like this, because really this is J, plus, and you can see the plus, but then you can see the minus. And the minus is really in the reactance, I believe, rather than changing this. We should always keep this the same. The definition of impedance is R plus JX. So we should always have that plus there, and then we should keep the minus in the reactance, 1 over omega c. And now we'll get into that. I'm going to stop this right here because this is the first one that I've done, and I'm hoping that when I replay it, everything will look good and my black pen will have come through, and it won't be such a gigantic thing that I won't be able to ever upload it onto YouTube or wherever it is I'm going to upload it. Probably YouTube, I guess. I don't know. All right.